What's up, Internet? Jeff Gretler, Head Brand Ambassador here at Spiceworks. Thanks for joining us today. We have a great show. Today, we're going to learn how to build a next-gen lakehouse, real-time analytics with Qlik, AWS, and Apache Iceberg. It's a great presentation, so why don't you check it out right now?
So thanks everyone for joining today. This webinar is titled Build Your Next Gen Lakehouse, Real-Time Analytics with Qlik, AWS, and Apache Iceberg. My name is Jason Hall. I'm a Principal Solution Architect with Qlik, and I'm happy to be joined today by Sati-san Wanadil from AWS. Sati-san's going to get our content started today, so I'll pass it off to him.
Thank you, Jason. Welcome everyone, and thank you for joining with us. In the first part of the presentation, I'm going to talk about data foundation, why the data foundation is critical for success, and then I will transition to Jason, who will present how Qlik is innovating with their open lakehouse on AWS. AI and generative AI are redefining what's possible for business. As we see today, our generative AI is driving innovation, which can transform organizations, how they scale their business and serve their customers. But one thing, their success depends on one critical factor above all, not just data or not just any data, but it is all about reliable, well-structured, and data which is accessible at scale. Now, that is why the data foundation is critical. As we all know, generative AI applications are still applications, right? You need operational databases to support the user experience for all interactions, which is outside invoking your LLM models. So analytics and data lakes are key because that is where you accumulate your domain-specific data, and these are the tools you use to explore your data to understand how to leverage your domain-specific data for AI and generative AI applications. So you need to source and integrate your data because data could be coming from different sources, right? It could be batch, it could be streaming, it could be structured data, unstructured or semi-structured. So you need to set up your data pipelines, and you need to keep up the data pipelines with the changing data. So you need to set up pipelines to transform your data and process it, right? So it becomes usable so that your downstream applications, whether it is an AI, ML, or generative AI applications, they can consume it so that you get the right information what business users or your customers are looking for. So it is not just about integrating data, right? You need to make sure that the data, what you sourced and integrated from different sources, they are governed. You need to make sure that it has got the quality what your organization needs. And you also need to make sure that the data is safe and secure, and it has got all the access controls which your company stipulates. So while it is always tempting to think that AI and generative AI are critical thing, it is really the data processes and the usage you need to nail down effectively so that you have a robust and modernized data architecture. Now, when we think about data warehouses and data lakes, they have evolved a lot, significantly over a period of time, right? So as data warehouses and data lakes evolved, the needs of the business users in terms of analytics needs also evolved. Early data warehouses, right? They focus on structured data and transactional systems for business intelligence and reporting. But as the data volumes grew, new technologies emerged to handle big data in data warehouses, and we started using technologies like massively parallel processing, columnar storage, data compression, so on and so forth. Likewise, early data lakes, they were, inexpensive, where organizations could store, data in any format. Data governance, metadata, and accessibility, they were all kind of afterthoughts, right? But over the past few years, data lakes have evolved to become more structured, and the term data lakehouse was coined to reflect, those features. Data lakehouse is nothing but, it's a combination of your data warehouse and data lake, right? Now, these days, if you really look at it, the real-time stream processing and machine learning capabilities are added to the data lakes so that it could support operational analytics, not just batch processing. And data lakes are increasingly deployed on cloud platforms for scalability and elasticity. As I mentioned earlier, in addition to the platform evolution, that is from data warehouse to data lakes, customer requirements have also evolved over the years. Now, customers want a single unified platform for analytics, transactional workloads, their AI and Gen AI workloads. Not only that, they need asset compliance, and they want the data platform to deliver an integrated governance experience. They need the real-time analytics and insight for compute resources which can scale elastically based on customer demand. And they also need the ability to handle a variety of data sources and formats, which could be structured, unstructured, or semi-structured. Now, the abundance of raw granular data in data lakes, of course, it enables more sophisticated analytics like machine learning and AI, which would not be possible in a traditional data warehouse. So, in a nutshell, the need for real-time schema on read, analytics at scale at lower cost is driving the adoption of transactional data lakes for modern analytics and applications. Now, as transactional data lake, kind of the schema on read architecture allows analysts and data scientists to quickly explore new data sets without lengthy and upfront data modeling. This definitely drives faster insights, right? Because data lakes have flexible schema, which allows for storing raw and unstructured data. And the schema is applied at query time rather than at ingestion time. That is a difference. That is what we call schema on read. And this is more adaptable compared to the previous rigid schemas we use in data warehouses. And not only that, the transactional data lakes, they offer a lot of benefits. For example, advanced analytics, they are lower cost, easy to scale, and they could offer real-time analytics, and above all, single integrated platform because it avoids silo data warehouses, data marts, and data lakes. And this consolidated approach enables governance, it avoids duplication, it improves data quality, making it cost effective so that the data analytics foundation paves the right benefit and throughput for your modern data architecture. And that is why right there the lakehouse come in. The lakehouse, it brings best of the both worlds, right? Data warehouse and data lake together. And they offer the benefit of being able to use for analytics and any kind of AI engines and tools of your choice on not just your structured data or unstructured data, on all the data without having to worry about data silos or fragmented governance. Now, to help overcome the challenges of data lakes, open table formats became very popular. These open table formats provide database like capabilities, not exactly, but database like capabilities, while still supporting storage on cost effective systems like Amazon Simple Storage Service, that is Amazon S3. And as you know, there are three popular open table formats: Apache Iceberg, Apache Hudi, and Detroit. AWS supports all three of these open table formats. Apache Iceberg is an open source transactional data lake which offers high performance format for analytic tables. Apache Hudi is an open source transactional data lake framework that greatly simplifies incremental data processing and data pipeline development. And Delta Lake is an open source storage framework that enables building a transactional data lake with compute engines including Spark, Flink, Trino, etc., and variety of APIs. So open table formats brings us many features such as asset transactions and record level operations, indices, concurrency control, schema evolution, and time travel. I'm sure that Jason is going to talk all these things in detail in his next session. But before I hand over to Jason, I wanted to mention that even though AWS supports all three of these open formats, which is Apache Hudi, Apache Iceberg, and Delta Lake, Apache Iceberg has emerged as the preferred standard, and AWS has fully embraced it. The primary reason is Iceberg brings the reliability and structure of a data warehouse into the openness and scale of data lake, enabling truly enabled, unified, governed, and high performance data foundation for your AI and analytics needs. So as we saw in the beginning, data foundation is critical to make your organization AI ready. Jason, over to you.
Thanks, Sathi-san. Really good stuff. So as introduced earlier, my name is Jason Hall, and I'm a solution architect at Qlik. Building upon Sathi-san's presentation, the reality of today's data architectures is that many of them are what I would call platform-centric. And that's an architecture where the data platform is the center of your data ecosystem. You're going to ingest all of your data into that platform, transform data within that platform, and then leverage that platform to consume the data. As Sathi-san mentioned, this leads to some inefficiencies around cost and flexibility of data. And really the reality is that most organizations don't have a single data platform. They've brought on different use cases over the years, different objectives that necessitate them to have multiple data platforms. Maybe you have one platform for your data warehousing and analytics. You have a second data platform for your Spark and compute workloads. And maybe even through various M&A activities or just changing requirements, you've brought on 3, 5, 10 different data platforms where you have to individually store, process, and consume data. This has led to significant pain points across organizations' data estates, from the cost and complexity of ingesting data into a variety of platforms, the high cost and complexity of transforming data within those platforms, and the risk that various platform-centric lock-ins are going to introduce into companies' objectives. And the reality of many of these pain points is that as low latency objectives become more common within organizations, these pain points and this extreme cost can even increase over time. So as a response to some of those pain points, and as Satya mentioned, Lakehouse adoption is tremendously accelerating within organizations, right? That interest in storing data in an open format and serving that data up across a variety of consumption engines is a really strong objective of many of our customers. And this was really validated by a survey that was done by Dremio in 2024. Fairly easy to find this survey yourself if you want to read more. But a couple of my key takeaways from this survey. One is that we are really at, I would say, even a tipping point of Lakehouse adoption accelerating. Over 2/3 of respondents to this survey predict that over the next 3 years, more than 50% of their analytics will happen within the Lakehouse. Right, so you can see this shift really happening within many of the survey respondents. Another takeaway I had that 86% of respondents said that their organizations have ongoing plans to unify their data analytics, right? Really to centralize their architectures to where their data within open Lakehouse formats will become the center of their data architectures. So Satya mentioned open table formats as a architectural shift that has really accelerated Lakehouse adoption. And Iceberg very much has become, if not the leader, certainly one of the leaders in the open table format space. Much of Iceberg's popularity is due to the specification that supports many capabilities that were simply not possible in prior Lakehouse formats. The Iceberg specification supports ACID compliant transactions. It also supports evolution of table structures, both evolution of table schemas as well as evolution of table partitioning. These types of evolutions in prior Lakehouse formats would have, in many cases, required a complete rebuild of the table, which in high-scale, multi-terabyte use cases may be at best inefficient and at worst impossible. And the Iceberg specification supports lots of capabilities that really have helped it gain popularity within the Lakehouse space. But Iceberg by itself is not magic, right? It's important to understand that Iceberg isn't a product. It's not a platform. Iceberg is a specification, right? It boils down to a definition and a set of best practices and a set of guidelines that define how to store your data and how to persist metadata to make Iceberg-specific functionality possible, right? So it kind of guides you to how data can be stored so that you can achieve ACID-compliant transactions in the data lake, how you can evolve schemas over time, and much more. Any solution that's built on top of Iceberg to deliver on an open lakehouse is going to have to leverage the Iceberg spec and of course adhere to it, but also provide capabilities that make that lakehouse functional across the organization. So for example, any open lakehouse solution will have to provide capabilities for data maintenance and optimization. Right? In other words, you don't just store data within Iceberg and expect it to work at scale. There has to be maintenance done to your Iceberg Lakehouse so that it delivers on the performance objectives that you have and so that it delivers on your cost efficiency requirements. An open lakehouse solution is also going to have to make sure that Iceberg functions across all of your data consumers, right? While much of the data marketplace has evolved to support Iceberg, there are varying levels of support across all of Iceberg's capabilities. So any solution that you implement that's going to store data in Iceberg needs to offer layers and functionality that make sure that that Iceberg data is available across all of its various data consumers through the syncing of Iceberg catalogs and the insurance that all of your Iceberg metadata is supported across all of your data consumers. Right, and something that's really core to Qlik, many of our customers require low latency and high scale ingestion. Right, many of Qlik's customers have been leveraging CDC-based ingestion technologies for years, some of them decades, and with a lot of CDC-based use cases, low latency is an absolute requirement. Right, low latency in terms of the scale that we can ingest data, but also the freshness of data when we consume it. And really a fact that's very clear in Iceberg once it starts being used for low latency ingestion is that performance challenges can persist or can be introduced when ingesting low latency data into Iceberg. And much of this is because of the Iceberg specification and how Iceberg stores data. I've got an architecture diagram over on the right. It's a high-level picture of how Iceberg stores metadata and data within a specific table. And one key takeaway about the Iceberg specification is that every time you write data into Iceberg, new data files are created that make up your Iceberg table. And for real-time data, you're going to have frequent writes to Iceberg, which are going to result in lots of small files. There's a common problem that's existed in the Lakehouse space for decades. It's often referred to as the small file problem. And this problem is effectively one where any Lakehouse table that requires you to query lots of small files, right? And when I say lots, I'm talking thousands, hundreds of thousands, oftentimes millions of small files. Querying that table is going to incur a lot of overhead simply in opening and closing files, right? Before you even read data out of those files, the simple API or the simple operation where you open a file and then close it when you're done is going to add overhead to your query performance. So with real-time data ingestion, when you end up with lots of small files over time, there may be a scenario where you have significant query performance overhead simply in opening and closing those files. Another challenge with Iceberg is that every time you write data to Iceberg, a new snapshot is generated within the Iceberg metadata. Right? And snapshots are a very important component of the Iceberg spec. It's one way that transactional consistency can be maintained. But again, for low latency and real-time workloads, where every write generates a new snapshot, over time, you could have hundreds, thousands, hundreds of thousands of snapshots that all have to be maintained within the Iceberg metadata. Right? And before any query that runs against Iceberg can even return data, it has to scan through the metadata to determine what files do we need to query in order to return that data. And so these very large metadata files can also add overhead to query performance. A third challenge with Iceberg, specifically around low latency and real-time use cases, is that the more data we write to Iceberg and the more frequent our data that we write to Iceberg, we may end up with lots of files that are no longer needed. Right? These files sit on disk, they sit within the object storage that our Iceberg tables are running on top of. And when we do frequent updates and end up with lots of unneeded files within our table, it can dramatically bloat the amount of storage needed by a specific table. Right? I've actually worked with customers before that ingested roughly 100 gigabytes of data into Iceberg, and they ended up with a storage volume of more than a terabyte. There's a variety of reasons why that can happen, but one is due to this frequency of writes generating lots of files that actually don't need to be stored. So again, at low latency and for real-time ingestion, all of these challenges need to be considered in order for an Iceberg table to be efficient, both in terms of query performance and the amount of storage that it consumes on disk. So again, because low latency is so important to Qlik, And because Iceberg optimization is a very hard problem to solve, Qlik actually made a very strategic acquisition earlier this year of a company called Upsolver. Upsolver is where I came from. And Upsolver had more than a decade of experience in helping customers solve many of these lakehouse-based performance challenges with low latency and high-scale ingestions. All right, so Upsolver Engine is what's now being integrated into Qlik to deliver efficient Iceberg ingestion and optimization. And where Upsolver fits into Qlik is a set of new capabilities built inside of Qlik Talon Cloud. Qlik Talon Cloud is Qlik's cloud-based platform for data integration and transformation, and the Qlik Open Lakehouse is a new set of capabilities built into Qlik Talon Cloud to help customers with Iceberg ingestion and optimization. Right? And this Qlik Open Lakehouse is based on the Upsolver technology that was acquired earlier this year. The objective of the Qlik Open Lakehouse at launch will be to offer 3 core capabilities. You'll see those mentioned here in the slide. And going through each of them, the first capability is high throughput data ingestion. All right, so you'll see a summarized list of ingestion sources over on the left-hand side of the screen. Maybe this is, for example, a high-scale CDC-based ingestion from Oracle, or ingesting data from your SAP systems, right? The Qlik Open Lakehouse is going to offer high throughput, very simple, low latency ingestion into Iceberg tables that are managed within your Qlik Open Lakehouse. Once data is then ingested into your Iceberg tables, the Qlik Open Lakehouse provides adaptive Iceberg optimization. This optimizer is what runs as a background service to ensure that the Iceberg potential challenges that could be incurred by low latency ingestion are challenges that you will not have to face. Right? So the Qlik Adaptive Optimizer will handle things like file compaction and file cleanups to ensure that your Iceberg Lakehouse is well performant and efficiently uses storage resources. And the third core capability offered by the Qlik Open Lakehouse is we're referring to it as data warehouse mirroring. This is effectively serving your Iceberg tables out to the data warehouses that you use in a form that can be consumed. Now that mirroring term there is really important. The mirror is not a copy of the data, right? It is simply a reflection of your Iceberg data as an object within your data warehouse that you can query with low latency and good performance, right? So for example, if you're a Snowflake customer, you're running Qlik Open Lakehouse, you can query your Open Lakehouse tables from Snowflake with minimal latency on data. So these are the 3 core capabilities that we're offering within the Qlik Open Lakehouse for high throughput data ingestion, adaptive Iceberg optimization, and mirroring of Iceberg data out to your data warehouses. And what this Open Lakehouse will offer you then is really that promise of making your data architectures more data-centric, right? Again, comparing back to the platform-centric architectures we talked about the introduction of this presentation, Iceberg can now be the center of your data architecture. And you can offer up real-time, low-latency data ingestion from real-time or batch workloads in a fully automated fashion that offers all of the capabilities of Iceberg, around schema evolution, partition evolution, into an Iceberg-based data lake. All of the ingestion workload can be handled without the need to run data warehouse compute engines. And the Qlik Adaptive Optimizer will ensure that that Iceberg data is optimized and well performant. And then that Iceberg-based data can be served up to all of your business use cases. Right? Whether that's real-time analytics, ML and Gen AI initiatives, data quality and governance objectives. Really, the data itself, the Iceberg data, can now become the center of your data architecture. So I wanted to dive down a little bit deeper on the adaptive optimizer that Qlik provides. I've often heard this referred to as the secret sauce that can make Iceberg successful within a data architecture. The adaptive optimizer runs as a background service against any table that you ingest data into, right? So while there's a lot of sophistication in the Adoptimizer itself, a key takeaway about the optimizer is that it's something that you get, right? It's not something you have to configure or tune or code yourself. Once you ingest data into Iceberg, the optimizer starts and takes action on your Iceberg tables. And there's a couple things that the optimizer is doing. The first is cost-based compactions. If you think about that small file problem that I introduced a few slides ago, compaction is a mechanism that allows for a lakehouse to solve that small file problem, right? At its core, compaction is taking lots of small files and creating larger files, right? And by doing so, you can reduce that file API overhead of having to open and close potentially millions of files. Now, in a perfect world, when you had an Iceberg table that had lots of small files, you would simply compact the entire table very frequently, right? Just compact all of the data all of the time, right? The reality, though, is that that's not practical. It's not practical from a resource consumption perspective or a cost perspective. And in many cases, it's not necessary either, right? So what the Qlik Adaptive Optimizer will do is it leverages a cost-based compaction algorithm where we first monitor and measure the status of an Iceberg table. And we understand through metadata analysis how many files you have, the size of those files, both average and max. And we leverage that metadata to predict what is the benefit that each compaction will give us. And then based on the outcome of that analysis, we prioritize then the most efficient and most effective compactions that we can perform, right? And then we leverage whatever available resources that you have in order to then deliver on those prioritized compactions. So the idea is your entire Iceberg estate is optimized, but we're prioritizing those that give you your best benefit. And eventually we'll get to all of the data over time, but we want to make sure that we're prioritizing where compactions are needed most. A second capability of the Adaptive Optimizer is dynamic partitioning. Partition management within Lakehouses has been a challenge for developers going back decades. Choosing efficient partition keys are critical to an optimized Lakehouse experience. And if you choose too few partitions, you'll end up with partitions that are too large. If you choose too many partitions, you end up with files that are too small. Right? So the Qlik Adaptive Optimizer has an approach to partitioning where we dynamically decide when and how partitions should be created based on the data that is ingested into Iceberg itself. It's a much simpler approach where you can let the Adaptive Optimizer determine when and how partitions should be created, and the optimizer will handle storing all of your data in the most efficient way based on that choice. The third capability of the optimizer would be intelligent file cleanups, right? And there's a couple different methods that we use for intelligent file cleanups. The first would be aggressive and efficient snapshot expiration. So based on your requirements, we will expire snapshots that are no longer needed, which then allows us to delete files which are no longer referenced by an active snapshot. We'll do that aggressively so that you can reclaim space on disk and keep your metadata scans as efficient as possible. Our file cleanups also delete what Iceberg refers to as orphaned files. Right? In order to maintain transactional consistency within Iceberg, Iceberg leverages an optimistic concurrency model where it's very possible that data can be written to disk that is not committed to the table. And so it's important that you clean up those files that were written but not committed, again, in order to keep the amount of volume on disk as small as possible. And so through these intelligent and efficient and aggressive file cleanups, we can make sure that your Iceberg Lakehouse is leveraging an efficient and small amount of storage. And lastly, I mentioned this when I introduced the Adaptive Optimizer. Everything that we've discussed here is automated. It's automated, it's continuous. It runs on your Qlik Open Lakehouse compute processes based on your scaling requirements. It will scale up to handle increases in data volume. It will scale down to conserve cost. and ensure that we're efficiently using the available resources that you've allocated in your Lakehouse clusters. So with all of that in mind, I wanted to do a quick demo. I'll kind of touch on those capabilities that we mentioned as available in the Qlik Open Lakehouse, specifically the simple ingestion of high volume real-time data into Iceberg, the optimization of Iceberg, and then how that Iceberg data can be leveraged across a variety of services, including some that run inside of AWS, as well as the mirroring of that data out to Snowflake. So let's go ahead and take a look. So here we have the interface to Qlik Talon Cloud, Qlik's cloud-based platform for data integration. And we'll start this demo by creating a new data integration project, specifically an open lakehouse project that ingests data into Iceberg and then optimizes your Iceberg Lakehouse. I'll give my project a name here. And as we scroll down, we'll see this is a data pipeline project with the data platform of Qlik Open Lakehouse. Now, the Qlik Open Lakehouse is going to require a few different connections that we use to process your data. The first is a connection to a data catalog. And in this demo, I'm going to pull up a connection to the AWS Glue data catalog. This is going to be our primary catalog supported at GA with additional catalogs supported to follow. And specifically, I'll grab this AWS Glue catalog connection here. A catalog connection is effectively a connection to an S3 bucket that we're going to store our Iceberg data in, and then an AWS IAM role that we can use to authenticate to the AWS services needed for data processing. The second connection here we have is a landing target. This landing target is an S3 bucket that we're going to use to store raw data in coming from our source. Right, this is data that's raw data coming from, in this case, our CDC sources, stored temporarily in S3, and that's where the Iceberg engine is going to pick up data from for processing. Right, so we'll define our landing connection here. And then lastly, we have our Lakehouse cluster. We'll talk a bit more about this cluster as we progress through the demo, but the Lakehouse cluster is a set of compute processes that run in your AWS account. So all of this is highly secured and very private because it runs in your cloud infrastructure. And the cluster then defines the compute resources that are going to be leveraged for Iceberg ingestion and optimization. So we've now created the shell of our demo project, and we'll now go through a wizard that allows us to step through the ingestion of data. First screen here is our data onboarding. And within the onboarding process, we're going to connect to our source system that we want to leverage for data ingestion. And in my case, what I'm going to do is connect to a PostgreSQL database, specifically this one. And that PostgreSQL database has a few tables that I will ingest into my Iceberg Lakehouse. Specifically this orders table and the sales info table. So we'll add those tables in. This could be 2 tables as I have here, or it could be hundreds of tables based on what you want to ingest. So a few different methods that we can use for ingestion. In this case, we want real-time, low latency ingestion. So I'll choose the CDC ingestion method. And you have a few different options for data onboarding. You can choose whether or not you want type 2 characteristics of your data to be ingested and made available. In this use case, let's say I do. I want a full history of change records accessible to my data consumers. So I'll include data with the historical type 2 data store. From here, we've got a summary of the project that I've stepped through, and we can now create each of the tasks. All right, so we've got our source over here on the left. The first task that we'll prepare is what we call our landing task. And this is what takes raw data from the source and stages that data in S3 so that it can be processed by Iceberg. We can open up the definition of this task, make any settings changes that might be needed or required by this use case. For our case, though, let's just take it as default, and we will prepare the task. This sets up all of the artifacts needed to ingest data from the source into our landing S3 bucket. So now that the landing task has finished preparing, we can go ahead and click Run and start the data ingestion from Postgres into our landing S3 bucket. Once landing is kicked off, we're presented with a monitoring interface that will help us track the status of our full loads and then eventually the process of CDC records as they move from source into landing. Going back to the project, now that landing has started, we can go ahead and configure our storage task. The storage task is what's going to ingest and process this data into Iceberg. I'll show you a few different settings here. For example, you can define task schemas that are leveraged inside of the catalog that you've configured to manage the Iceberg metadata associated with your tables. In this case, because I'm using the Glue catalog, these are schemas within AWS Glue, which will present the tables out to whatever your query engine is, whether that's AWS Athena or SageMaker or any supported AWS service. You'll notice two schemas, one for the data itself, which we call the task schema, another for internal data that's used to represent the raw change data records that are available within Iceberg. We can set up prefixes if we want to avoid table name conflicts, and again, choose whether or not we want historical data to persist within these objects, specifically your type 2 characteristics of your ingested data. But in my case, though, like I did with landing, I'll go ahead and prepare the storage task, which will set up the artifacts needed for Iceberg ingestion. And then once the preparation step is complete, I can go ahead and start the ingestion of data from landing into these Iceberg tables. We've now finished preparing the storage task, so I can click Run to start the Iceberg ingestion process. Like with the landing task, we do have built-in monitoring that can be looked at to track the status of your Iceberg processing. We have interfaces here which will show you the status of full load, as well as the status of CDC changes being applied to each of the target tables. So just that easy, we now have a project created that is ingesting data from our source Postgres system into Iceberg tables at low latency and near real time. Right? So this project will just run in the background, leveraging the Lakehouse cluster that we've set up associated with the project. For a bit more visibility into that cluster, let me show you here the Lakehouse clusters view. Again, remember, this cluster runs in your AWS VPC. So it's under your security controls, within your network firewalls, and it's really the way that most of our customers are going to require us to process data, right? No data that you process with the Qlik Open Lakehouse leaves the network security of your AWS VPC. And when we look at a Lakehouse cluster here, you'll see a few different properties associated with it. First of all, the cluster is running and the number of instances it's running with. These clusters are going to dynamically scale to handle the amount of data that needs to be processed, right? Our clusters are running under a specific machine size, in this case, 4x large, and we've configured our clusters to run with between 1 and 8 spot instances. For those unfamiliar with spot instances, they offer the least costly price for AWS compute, right? Spot instances can basically go away at any time. AWS reserves the right to take away a spot instance, and we've built the Qlik Open Lakehouse cluster engine to be able to support these terminations of spot instances with low latency, right? So spot instances is one way that we achieve cost efficiency within your Open Lakehouse. You'll also see a scaling strategy that can be applied here to your cluster. These are a few different algorithms that we provide that control the aggressiveness with which clusters will scale to handle increases or decreases in data volume. Right? Let's say you've got a real-time data ingestion happening, and all of a sudden you rebuild one of your source Postgres tables and load in 50 million records, right? How aggressively do you want that cluster to scale up to handle that increase in data volume? The low latency model is one that scales relatively aggressively so that we can handle that increase in data volume with minimal impact on data freshness. We also, within a cluster definition, do support a few different scaling models. We do support a low cost model for those users or those use cases where you might want to sacrifice data freshness to keep costs as low as possible, right? It's a less aggressive algorithm. And then we also have a model we call consistent low latency, which is the most aggressive scaling that we can perform. There's even manual scaling options that do exist. If you can predict increases in data volume, you can manually scale a cluster so that you're prepared to handle that increase. But again, everything that you see here is happening 24/7, automatically, all of the time, with minimal, if any, user input. So very much a very simple, very set it and forget it approach to Iceberg ingestion. So we've set up the initial Postgres project. I also want to take the opportunity to show you a project that I've had running here for a bit, because it'll allow us to see kind of the impact of optimization. Now, this is a project that's reading data from Oracle, about 9 tables being ingested into Iceberg from an Oracle source. And if I look at the monitoring screen for this project, we can see this concept here of, in the CDC status view, changes that are incoming, changes that are processed, and then changes that are optimized. Right? Incoming changes have been received by landing, but are not processed into Iceberg yet. Process changes have been processed into Iceberg. Once a change is processed by the Open Lakehouse, the result of that change is now queryable by whatever engine you're using. So in other words, your data will be fresh as to the result of that process change. And then once the change has been processed, it then will eventually become optimized by our adaptive optimizer. So changes that are processed but not optimized will be accessible, but the performance may not be as good as it can be. Once changes are fully optimized, you'll know you're getting the most efficient possible performance. In this example, you can see that all changes that have been processed have also been optimized, but you can use this view to track the status of changes as they move from landing into Iceberg and then through our adaptive optimizer. Now, the last function I do want to show you within the Open Lakehouse demo is that ability to mirror data out to your data warehouse, right? The storage task is writing data into Iceberg, but what if we want this data to be queryable by, for example, Snowflake, right? We have the option of creating a mirror task in Qlik Talent Cloud. And the mirror task, I'll show you the settings here, simply point you to Snowflake using a Snowflake connection that you've created in QTC. You will also provide a Snowflake schema that you want our objects to be managed within. And then down below, you have 2 different options for the mirror table refresh. Again, remember, a mirror in QTC is not the copying of data. It's simply the creation of a Snowflake object that reflects your Open Lakehouse tables. Now, within Snowflake, whenever you create an external Iceberg table, which is what these mirrors are, you have the option with how often and how you want Snowflake to refresh the metadata associated with your Iceberg table. The option that you see I've chosen here is a Snowflake managed refresh. This is automated. It happens fairly often in near real time, and oftentimes is the simplest way to refresh your Snowflake metadata. In other words, you're kind of letting Snowflake handle the metadata refresh. It's an auto refresh option, and it's going to service the majority of your use cases. The downside of the Snowflake managed metadata refresh is that we at Qlik and in QTC have no control over when those metadata refreshes happen. So we can't ensure that data is consistent up to a specific point in time. And that is especially important when you're doing transformations on this data, especially transformations that require data to be consistent to a particular point in time. So for that sort of workload where you do need to ensure and guarantee that data is consistent to a specific point in time, we support a Qlik managed table refresh, which you can either run manually or you can schedule. And the nice thing about the Qlik managed refresh is that if you choose a schedule of, let's say, 5 minutes, you will know that your table data is consistent to a 5-minute point in time, which again will give you more consistent transformation capabilities on that data. But you can choose, do you want the Snowflake managed or the Qlik managed refresh option? But with this mirror task set up, now continuously as data is ingested into Iceberg, the Snowflake mirrors that we've set up can query that Iceberg data with minimal configuration and low latency. Now, to showcase that querying, I'm going to go ahead and just switch my interface here into AWS, right? And again, I wanted to showcase the fact that AWS native services can now query this data that Qlik is ingesting into and optimizing within your Iceberg Lakehouse. I'll start here by showing an Athena-based example. So here you can see the OLH benchmark schema that I've set up in my storage task. We've got a table here, this order line table coming from Oracle, and I can now query this data and see the results of this data in near real time have been ingested into my AWS infrastructure and queried by Athena. And anything that leverages the Athena engine will gain the same level of compatibility. For example, if you're using AWS SageMaker Lakehouse, you can query using SageMaker Studio the Qlik Open Lakehouse tables since Iceberg is well supported within SageMaker itself, right? But really our integration here with the AWS Glue catalog and with AWS Athena as an example query engine here gives us very broad compatibility within a range of AWS services for data consumption. Now, similarly, we can leverage Snowflake. Again, because we're leveraging the Snowflake mirroring capability that the Qlik Open Lakehouse provides, we can take that same query that we just ran within AWS Athena and run it within Snowflake and see the data represented here as well. And this is a very common use case that we see with customers. They might want to use something like AWS Athena for ad hoc data investigation, right? If we're doing data forensic against our bronze layer in our Open Lakehouse, we might use Athena for that sort of investigation. But for our business analytics that we're serving up to end users via dashboards, we might leverage our Snowflake investment for that type of data consumption. But with Open Lakehouse, we have the same data, literally the same tables that are servicing up both use cases and both query engines. And that's really a demonstration of the value that these Lakehouse-based architectures can provide across a variety of data use cases. In this case, we've shown you two different engines querying the same data, but we're having customers that are showing interest in potentially dozens of engines, all having access to the same Iceberg data within their Qlik Open Lakehouse. So just to summarize what you've seen in this demo of the Qlik Open Lakehouse within Qlik Talon Cloud, we started by very simply setting up an Open Lakehouse project that ingested data from both PostgreSQL and Oracle into Iceberg tables. We set up that data ingestion with a change data capture-based solution for real-time ingestion into our Iceberg tables. And we optimized those Iceberg tables continuously using our adaptive optimizer so that we had very efficient query performance and leveraged an efficient amount of storage within our Iceberg estate. We then leveraged a variety of services to query the Qlik Open Lakehouse Iceberg tables, specifically AWS Athena, which is again supported well across the AWS ecosystem. And then we also set up mirrors within our Qlik Open Lakehouse so that that data could also be queried by Snowflake. If you'd like to take advantage of the Qlik Open Lakehouse in your environment and take advantage of all the capabilities that we've demonstrated, we're looking to go GA with the Qlik Open Lakehouse later this fall. And you can see a bunch of resources available to you here on this slide, both a blog announcing the launch of the Qlik Open Lakehouse, as well as some white papers that might help you if you're just getting started in your Iceberg journey. And then the last QR code there is to the product website where you can learn a lot more about the Qlik Open Lakehouse, as well as sign up for more information and to get the Qlik Open Lakehouse technology into your own hands. So I appreciate everyone's time and attention on today's webinar. I want to thank Sathi-san for representing AWS and getting their perspective on Iceberg within the AWS ecosystem. And then I hope everyone has taken away from this webinar some useful information that can help you hopefully plan out your Iceberg initiatives within your organizations. So thanks everyone again for your time and hope you have a good rest of your day.